let's look at Snell's law a little more closely. We have n1 sine of theta 1 equals n2 sine of theta 2. Okay? Now, what's n1? What's theta 1? It's really good to have a picture of this. Let's go ahead and choose a bath of water. So I've got n of water and n of air. Okay? Now, I'm going to say, what if I shine light from inside the water, shine it towards the surface? Okay, in that case, 1 is the water, and 2 would be the air, because the light is coming from the water and out. Okay, so if I make an angle, here's my light going upwards, this angle here would then be theta 1, and I know it's going to bend further away from the normal, making theta 2, because I know N2 is air, which is 1, and N1 is 1.33. It's water, and when light travels from a material of higher index of refraction to lower, then it bends away. Okay? If I had light traveling from a lower index of refraction to a higher index of refraction, it bends towards this normal. So in this case, we're traveling out of the higher index material, so we're bending away from the normal, as you can see there. Okay, and Snell's law would show that if n1 is bigger than n2, then theta 2 should be bigger than theta 1 to offset that, to create this equality. Okay, so with that being said, what if I make theta 1 a little bit bigger? Well, theta 2 is going to get bigger, but it's going to get bigger faster because it bends away. And if I keep making theta 1 bigger and bigger, theta 2 eventually is going to hit 90 degrees. When theta 1 still is, it's far from 90 degrees, because theta 2 has to be bigger than theta 1. So there's an angle, there's some angle which we call the critical angle, theta critical, okay, in which the refracted ray is just barely skimming the surface. So that's a refracted ray. So theta 2, right there. It's 90 degrees. Okay, well that means we can find theta critical. We can find that, plugging it up here. So we have, remember this is N1 and N2. Oops, N2. So we have N1 sine of theta critical, that's N1, that's theta 1, equals N2 sine of theta 2, but sine of 90 is 1, so that just goes to 1. And so I can divide the N1 over and do the inverse sine to get theta critical equals inverse sine of N2 over N1. Okay? Now let's just do a little note of math versus physics. Okay? We've observed physically through experimentation that when light travels out of a medium of high index of refraction to a medium of low index of refraction, it bends towards or away from the normal. Okay? And so the theta critical, the only way that can happen is if N2 is less than N1. Alright? That's how theta critical happens if N2 is less than N1. Well, mathematically, the argument of inverse sine must be a fraction less than 1. Otherwise, it doesn't work. It has to be a fraction less than 1. So this is mathematically correct, and also another way to help me check my physics. If I write, if I memorize this equation, which you need to memorize this equation, and then apply theta 2 equals 90. Okay, but if you think about this one, think, oh, which one's the N2 and N1? The only way this is going to work if this light is traveling out of the higher index material. Okay, so that's a nice check of the math with the physics. Okay, so this is called the critical angle, and we call this total internal reflection because no light, if you go slightly above theta critical, no light's getting out. The question is, where's all that light going? Well, this is super cool. Okay, so you can think about, you're in this state right here. You're slowly increasing theta 1. Theta 2 is slowly increasing as well, but kind of at a faster rate. And it gets to this point right when theta 1 equals theta critical. And then you take theta 1 just slightly beyond theta critical. Suddenly, all the light snaps into reflection. Okay, well, that is the same. Okay, that is the same angle, because that's the law of reflection. This is really cool. The light was slowly transitioning from some angle here to 90 degrees, and then suddenly snap. It snaps down to that angle in total reflection. Nothing is transmitted out. Nothing is refracted. It all is reflected inward. And so that's why we call it total internal reflection. This is a critical angle that gives you the bound for total internal reflection. It's a really, really cool principle. Okay, and the reverse of this, there's something that's really cool that I invite you to look online. It's called Snell's window. And if you have a chance to go to the swimming pool and sink to the bottom and look upwards, or if you have a really cool chance of going to clear crystal water somewhere in the world and be able to look up, you can see a really cool application of this called Snell's window. So at this moment here in Indiana, you might have to just look online to see the beautiful pictures, but sometime in your life you'll have to take the chance to go down to the bottom of the pool and look up and see total internal reflection happening in that process. Okay, total internal reflection is when theta 2 is 90 degrees and all the light then is reflected inward.